Welcome back, everyone. This week we have quite a bit to cover in this lesson, and this lesson is about functions. So take a minute to read through the information on this page, go through the objectives, the vocabulary, and then read about if something is a relation or a function, domain and range, and then function notation. And when you are ready, you can continue the video and I will try to explain all of this to you. The first thing we want to talk about is a relation versus a function. And if you remember from the first page, a relation is just a collection of ordered pairs or a set of ordered pairs. And a relation can have any sort of numbers in the x and y values. And it doesn't matter if the x values repeat and it doesn't matter if the y values repeat. But in a function, what's really important about a function is that the x values do not repeat. So the key thing to look for if we want to determine if something is a relation or a function is this last sentence. If there are any repeating x values, then the relation is not a function. Okay, so the thing we have to do is just take a look at the x values. So if we look at this first set of ordered pairs, we can see we have -2, -1, 0, 1, and 2 for our x values. And since none of those numbers repeat, that means that this is a function. So we can go ahead and call this one a function because every x value has exactly one y value associated with it. Okay, if we look at the second one, we have 2, 1, 2, and 3. And you'll notice I said 2 twice. So saying 2 twice is a bad thing when it comes to a function. So this is just a relation because 2 results in a y value of 5 and 2 results in a y value of 15. So this would be just a relation, not a function. And the last one, we have 0, 1, 2, and 3. So you'll notice I didn't repeat any numbers for the x values, so that means this is a function. Okay, so it's really important to be able to identify if something is a relation or a function. And with the case of ordered pairs, we simply just look at the x values to see if anything is repeating or not. Now, if we change it up a little bit, and we don't have ordered pairs, if we have a graph of some sort, we don't have the luxury of being able to look and see if the x values are repeating. But there is a way that we can identify if a graph is a relation or a function really quickly, and that is by something called the vertical line test. So all we have to do is draw a vertical line, and so you can imagine we have this vertical line here, and if we slide that vertical line back and forth all across our blue line that we have on here, you'll notice that it only touches that blue line at one point at a time. And if it only touches that blue line at one point at a time, that means that this is a function. Okay, so if we move down to the next one, if we draw a vertical line through here, you'll notice that it crosses the blue line in 2 different spots at the same time. And because of that, this is not a function, this is a relation. So we call this the vertical line test, and you can do this with any graph. You can draw a line, a vertical line, slide it back and forth, and if it only touches the graph at one point at a time, then you know it is a function. So we can do the same thing here if we imagine sliding that back and forth. Now this one curves around quite a bit, but it never touches that line at more than one spot at a time. So this is a function. And then similarly down here, this is actually called a parabola that's laying on its side. And if we draw a vertical line, we will notice that it crosses that parabola in 2 spots. So therefore it is a relation and not a function. And it's the same reason when we have ordered pairs. If we have a vertical line that touches the graph at more than one point, that means that the x values do not have exactly one y value output. So in this case, the x values have 2 outputs. So if we looked at this one on the lower left-hand side, the red line is approximately going through 4, and If we look on the graph, that we have a y value of 5.5 and a y value of negative 1.5. So we can't have two y values associated with an x value. All right, so those are the two different ways we can identify if a relation is a function. Another thing we need to be able to do is just use function notation. So a function is kind of like a machine where we take an input of some sort, we put it into one side, and it comes out the other side as something different. Okay, so if you remember from the beginning, function notation, it's written like this, where we have an f, parentheses, and an x, and it simply tells us that we have a function named f, and it's of the variable x. So whatever variable is inside the parentheses, that's the variable for our function, and the letter that's outside of the parentheses, that's simply just the name of the function. We just use that to identify that this is the function f. And the way we say it is we say f of x. Okay, so it's a function of x, basically. And that f that's out in front, in this case it's an f, but we could have any letter out front. So we could have g of x, h of x, all different numbers outside. The problem with function notation is sometimes people get it confused with multiplication. They think that it's f times x, but it doesn't mean we multiply f times x. It's simply just a notation that's telling us that we have a function. Okay, and the important thing is the number in the parentheses is the number that we're going to substitute for x in the function. So if we want to evaluate a function at a specific number, what we would do is we would put that number inside the parentheses where it says f of x, and then we would also substitute that number in the function on the right-hand side of the equal sign. So if we want to evaluate the function f of x is equal to 2x plus 1 at 2, we would write f of 2 is equal to 2 times 2 plus 1, and then f of 2 is equal to 4 plus 1, and then f of 2 is equal to 5. And then we would always write our answer as an ordered pair, because with a function, what we're doing is we're putting something in, we're getting something out, so we want to identify the two things that we're putting in and getting out. So in this case, it's the 0.25. Okay, so let's put this to practice a little bit. So if we want to evaluate a function, it says let f of x equal 3x squared minus 5x. Well, we can evaluate that function simply by writing f of 2 is equal to, and when we have that 2 in the parentheses, that means we're going to replace the x in the function with 2. And you'll notice that I do it with parentheses, so 3 times 2 squared minus 5 times 2. And this is one that people really get confused with sometimes, and parentheses are hopefully going to help you. We do the exponent before we do the multiplication, so we have 3 times 4 minus 10. And then 3 times 4 is 12, so we have 12 minus 10, and 12 minus 10 is 2. So we would write our answer now as the 0.2 comma 2. So for f of 2, we would say it's 2 comma 2. Okay, similarly, we have f of negative 8, so we're going to do the same thing. We're going to substitute negative 8 into the x values in the function. So we have 3 times negative 8 squared minus 5 times negative 8. Okay, so again, we do the exponent first, and if we're taking a negative number and squaring it and it's inside parentheses, that's going to become positive. So we have 3 times 64 minus 5 times negative 8. 5 times negative 8 is negative 40, and if we're subtracting negative 40, we're actually going to be adding 40. Okay, and then 3 times 64 is 192, so we have 192 plus 40. And then 192 plus 40 is 232. So we got actually a pretty big output here, but that's okay. It's just another number. So we would write this as the point negative 8 comma 232. Okay, so that's one example where we have a simple function 3x squared minus 5x. We can continue and take a look at another function. If you remember from earlier in the year, we talked about what these parallel bars on the outside of an expression mean. They mean absolute value. So basically what that means is whatever we get on the inside, whether it's positive or negative, we're always going to write our answer as positive. Okay, so if we have, in this case, our function is g of x, so it's a function g, the variable's x, so we have g of negative 5, so I'm going to go ahead and substitute a negative 5 in for my x, and I'm going to simplify things, so I have negative 7 times negative 5 is positive 35, and 35 plus 4 is 39. And in this case, the absolute value isn't going to matter because we have a positive number on the inside, so we know the absolute value of 39 is 39, so we're just going to leave that as 39. But then we're going to write our answer as a ordered pair, so we write it as negative 5, comma 39. Okay, so there we go. That's an example with an absolute value function. Now let's do the same thing, but in this case we're going to evaluate the function at 2, so we're going to say g of 2 is equal to the absolute value of negative 7 times 2 plus 4. Negative 7 times 2 is negative 14 plus 4. And now since the negative number is bigger than the positive number, we're going to end up with a negative number inside of our absolute value, so we end up with negative 10. And the absolute value of negative 10, so this one, the absolute value is going to make a difference, and it becomes positive 10. So our ordered pair is 2, comma 10. All right, so another example of how we can use function notation to evaluate a function. All right, let's keep going here. Another thing we need to know about functions is I talked about the idea of inputs and outputs. We have a specific name for the inputs and outputs, and in this case, the input is called the domain, and the output is called the range. And it's really easy to kind of get those two mixed up. And so it's just something that we kind of have to memorize. The domain is what we put in, the range is what we get out. And when I say that, what I mean is the x values represent the domain and the y values represent the range. And so all we have to do if we're given a set of ordered pairs is identify the x values, identify the y values, and we know what the domain and range are. So again, I can use my highlighter to just highlight the x values. And I can say, all right, the domain is the set. So we're going to write it in set notation. So we're going to have a set of numbers. We're going to say negative 2, comma negative 1, 0, 1, and 2. And we use those curly brackets on the outside to represent a set. So here's the domain. It's negative 2, negative 1, 0, 1, and 2. So those are the x values. And then the range is all the y values. So again, we're going to write a set. So in this case, it's 2, 3, 1, 4, and 5. Okay? All right. The next one, we have domain and range. So the domain, the x values, we have 0, 1, 2, and 3. Okay, so we can write that as a set for the domain. We have the set of 0, 1, 2, and 3. And then the range, we can look at that and say it's 5, 10, 15, and 20. So for the range, we'll just write that as a set again. 5, 10, 15, and 20. All right, it looks like I didn't add enough spaces here, so my title from the next page is at the bottom of this one, but that's okay. We can deal with that. Another thing that we have to do is sometimes we won't have ordered pairs to take a look at and identify the x values and the y values to look at our domain and range. So if we're looking at a graph and wondering how to find the domain and range, all you have to do is remember that it's still just the x values for the domain and the y values for the range. So the x values are left and right, the y values are up and down, but we need to remember that lines go on forever sometimes. So we're going to end up with positive and negative infinity as part of our domain and range sometimes. Okay, so what I'm going to do is actually start with the one on the far right, because this one does not continue on forever. It's a segment that has a beginning and an end. So what we need to do is just identify the domain. So the domain is the x values that we have as part of our function. So the thing we can do is we can say, all right, my domain, it starts here at -3, right? And it goes all the way over to +1. So the domain goes from -3 to 1. And the solid little dots on the end means it includes those numbers. So my domain is -3 to 1. So I used a bracket to say that I'm including those. And then my range is the y values, right? So I'm going to do the same thing here. So it goes from -2 to +4. So this is my range from -2 to +4, and it includes those numbers because of the solid dots on either end. So I have -2 to +4. So this is my range, and then I'm going to put that R or that D in front of the other one for domain. So here we go, domain and range. Okay, so sometimes people get a little confused about this. I'm not exactly sure why, but just remember that it's x values for the domain and y values for the range, and you should be okay. All right, I'm going to go to the middle one next. The middle one, we can't really do what we did like we did on the right-hand side, because this is a line that continues on forever. And if you imagine from an x value perspective from right to left, this line is going to keep going and going and going in both directions. So it's never going to stop. And that means we can always just continue to go one more number to the left or one more number to the right. So that means that our domain is going to go to -infinity and also +infinity. Okay, so our domain is simply -infinity to +infinity. Okay, and similarly with our range, we have a range that the line continues on forever. So same thing with y values. We could just continue to add a y value as we go up or a y value as we go down. So we're going to go to +infinity here, and we're going to go to -infinity here. So our range goes from -infinity to infinity. So basically what this is we have a line that we can put any x value into the function, and we're going to get a y value out. So we can pick any x value we want, from +infinity to -infinity, and we're going to get some number out between +infinity and -infinity. Okay, so these are two basic examples. One where we have fixed endpoints. So like the first example on the right, we have fixed endpoints, and then the example in the middle, we have no endpoints. It just continues on forever in both directions. And now the third one, or the one that's on the left, is an example of one that kind of combines those two. Now, the thing we have to be careful with here is if we think about our x values, if we think about going this way and going this way, since we have those arrows, and this is not, these lines on either side are not parallel to the y-axis, they are going to keep going, and it's going to continue to go to the left just a little bit at a time. And the further we go, the further it's going to go to the left. So for this one, the domain is going to go from -infinity to infinity. So we can go ahead and write that domain as -infinity to infinity. Okay, but with this one, the range is a little bit different. The range, you'll notice that we have an endpoint for the range right down here. It doesn't get any lower than -3. Okay, so we can immediately go in there and say, hey, it goes down to -3, and it actually touches -3. So we can say, all right, so it includes that -3. So we're going to start at -3. But then we'll notice these arrowheads pointing up. We know that this thing continues on forever up. So that means it goes to +infinity. So in this case, we have a domain that is any number x from negative infinity to positive infinity, and then the range, though, is bound on one side by that negative 3, but goes to positive infinity. Okay, so I think that's it.